Você pode pegar aí. Pode começar. Tá bom, Good morning, everyone. Welcome to this morning session. Today we have a Valencian session for this morning session. And it's a pleasure for me to introduce my former student, recent PhD, Ignacio Breva Ribes from the University of Valencia. And he's going to talk about the work he's done in his thesis, in part of it, not everything. In particular, he'll talk about augmentations of singularities and quasi-homogeneity.
Thank you very much, Raúl, for the presentation. And, well, thanks everyone for coming, and thanks to the organizers for inviting me to this very special workshop in honor of Cidinha. I had the pleasure of sharing 2 doctoral stays here at the ICMC, working with her. And sadly, I have no photos of this this time, but I have a lot of memories because working with her was a really important moment, a really interesting time, not only mathematically, but also personally. She was a great person, and we will deeply miss her. So, okay, as Raúl said, I'm going to be talking about some of the work from my thesis, mainly in 2 blocks: augmentation of singularities. I'm going to be talking about a special kind of map germs, a special family of map germs from which I will explain how to build later. And then I will talk about quasi-homogeneity of map germs in general. And the thing is that the 2 blocks share a common philosophy, which is that I will try to recover information of the map germ, of a given map germ, from its stable unfolding. So to each singularity, I will associate, well, there is associated, I will not, somebody else did, matter in particular. I will associate a stable singularity, and I'll try to recover information from it. And this is what joins both of these topics. So I will do a general introduction. I will call it recovering data from stable unfoldings. Maybe I realized yesterday that maybe this is a bit trivial, but I think it's good that everyone is on the same page. So I hope that nobody minds if I go on some things that are a bit basic. So my setting is that I will be studying map germs from Kn to Kp. K can be real or complex, and they will be smooth, so holomorphic in the complex and infinity in the real case. And I'm interested in map germs up to A equivalence, so up to equivalence in source and target by diffeomorphisms. Okay, so 2 map germs are A equivalent if they satisfy this kind of diagram with diffeomorphic columns. Okay, so of course the goal when you have an equivalence relation is to find all possible equivalence classes. And the way by which we do this is by perturbing singularities or deforming them. So mainly I work with something called unfolding. So an unfolding in n parameters of F is any map germ of this form. Okay, so any map germ that just has a family of deformations of F. So here F0 is again F. And then we attach the parameter space to the right so that we can glue together all the family. And I just put an example, which is the classical example, which is, of course, the cusp. In this example, you have the classical family of deformations of a curve on the left. And for different values of the parameter, you have different images. And you can glue them all together into a single map germ, which is the unfolding, okay? And the idea is that unfoldings are again map germs, and that you want to study them as map germs and try to recover as much information as possible. So this is not any unfolding of the cusp. It is called it is what is called a versal unfolding. So it is a very nice unfolding because it encodes all the relevant deformations of the cusp. Okay, so the ideal case when you're studying a map germ is that you can obtain its versal unfolding, and then you can study its neighborhood, and you can understand what happens when you perturb it. And the way in which you do this to obtain, I'm not going to define what a versal unfolding is, but to obtain a versal unfolding, you just need to think about it as the best possible unfolding that you can ever think of. You need to compute this space, this algebraic space, this module. Okay, if you find representatives of these generators, if you find vector fields whose representatives generate this quotient, then you can build a versal unfolding. And then we define the A codimension of F as the dimension of this vector space, okay? So this does not need to be finite, but if it is, then you can build the unfolding. And as you will see, this mixes two very different modules, because this is a module over functions in the target. This is a module over functions in the source. It can also be seen, of course, as a module over functions in the target, but in general, when you do that, it's not finally generated. So this is a pain to compute in general. There are some algorithms, mainly by Kirk, using complete transversals, and then recently by Afzal, Diva, and Pfister, also doing kind of a degree-by-degree way to compute them. And recently with Peñafort Sánchez, and together with Teramoto, Marco Buzunariz, and Matthias Stack, we are trying to find another algorithm which does not necessarily go layer by layer, but that it tries to do it as a whole. We still are working on it. We have some nice results, but if anyone has found any modules which mix two rings through the action of a mapping, then we would like to know, just to know if we can share opinions and find common points to work with. So, okay. So yeah, as I said, this is very difficult to compute, but it is what we would like to obtain. And luckily, there is an easy way to compute it. Well, easy. There is a way to compute it, which is through the stable unfolding. So to obtain a stable unfolding, first definition, a stable unfolding, an unfolding, well, a mapping is unfolding. A map generally is stable, is stable. If small perturbations do not modify, change the A class. Do not change its A class. So of course the CASP is not stable because I modified it a little bit and a double point appeared, so clearly not stable. But here the unfolding, this unfolding is stable. This is a cross cap, and it is stable. You cannot modify it in any relevant way. Okay. So okay, how? Okay, so if I'm given a map germ, I can associate to it a stable unfolding in the case that this module is finite. So to obtain a stable unfolding of F, I can compute this module right here. Okay, so I have a map germ that is not stable, but I can compute this thing. And if this thing is finally generated, then I can use it to build a stable unfolding. And this is much easier to obtain than the A normal space because this is an OM module. And you can put it into Singular or your algebraic computational algebraic program of choice, and it will do it in a second if you do not put something that is huge. Okay, so since this is easy to compute, I would like to obtain information from it. And the way to do this is by using Damon's theorem. So I'm going to erase this blackboard because I do not want to cover this one. And to present Damon's theorem, I need to define something first, which are liftable vector fields. So, definition. I'm always assuming that F is a smooth map germ throughout the whole talk, but I'm going to write it again. If I ever forget to write this, recall that F is a map germ between K and KP in general. We say that a vector field in the target and a vector field in the source are F related. If they satisfy this equation. Okay, and if they do, then we say that this is liftable and this is lowerable. Okay, so the set of liftable vector fields of F is just the set of vector fields in the target that are liftable for F. Okay, and similarly for the lowerable vector fields, but I won't be using that set. So then I can write the following theorem. By the way, if at any point anyone has any doubt or anything, please feel free to stop me and to ask me to repeat things if I'm going too quickly or anything. I would be glad to answer. So given this definition, I can present this theorem. Originally, the first version by Damon in the year 91. And then later, the best version that I have found is by Mon later in 99. Maybe there are other places in which this has been proven, but I think this is the next one. So, and it's the way that I will present it. This theorem tells you that, okay, if you have a diagram like this, this is a P. Okay, if you have this diagram, and this is a Cartesian diagram, and H is stable, then the A normal space of F can be recovered from the data in this diagram. So this is isomorphic to this thing right here. Okay, so this is exactly what I was commenting at the beginning. So you can recover the A normal space from the stable thing. Okay, so this is great because, in particular, if your map germ admits a stable unfolding, then of course you can build this diagram. I think I'm just going to be using these two blackboards. Oops. Of course, if F is a stable unfolding, you can always write F Kp times Km Okay, so this diagram is always Cartesian. So in particular, from a stable unfolding, you can always recover the A normal space of your map germ. So this is great news. Okay. One of the things, well, what we're going to do is to use this to study a particular type of singularities called augmentations. Someone that did something similar is Sherland in the year 2014. She used this theorem to find lots of examples doing curves, doing pullbacks using, instead of putting here a 0, she put here a curve over the parameter space. And she used this to obtain several families of examples satisfying what is called the Monk conjecture, of which I will be talking in a bit. And she found lots of very interesting examples with like huge codimensions, and it's a really nice paper. But when working with curves, the module presented by the Monk theorem is also a bit difficult to tackle. And then when you do a different thing, which is instead of doing curves using functions, you get what are called augmentations, which I will present in a moment, and they behave much better. So this module behaves much better in that case. So I'm going to just present the object and stop talking in general about it. So what is an augmentation? Augmentation. An augmentation is something that is built from three things. You get first a map germ, smooth map germ. You assume that it admits a one-parameter stable unfolding. One parameter. So I will write by the letters to make it brief. So an unfolding in one parameter, which is stable itself as a map germ. Okay. This is a strong condition, but as we will comment in a moment, they are pretty common still. And then you get a third element, which is a function, a smooth function. Sorry, not C, but K. In principle, not necessarily with isolated singularity, but in practice, if you want things to have finite codimension, then this will need to have isolated singularity. Okay, so when you have these three elements, you can build an augmentation, the augmentation of F by F and G is this thing right here. We use compose the function on the parameter space of X, and then attach the variables of the function as the parameter space. So augmentations are just another unfolding, a different unfolding of your map germ that in general, when G is not regular, this will not be stable again, but they can be constructed in this way. And so, of course, the philosophy with these things is that, okay, if I find something like this, how can I understand the information of this mapping from its base elements, okay? How can I recover the data that I want? And we will see that we can actually recover most of the data, and this makes augmentations a great way to construct families of examples in which to check things easily. And not only that, but augmentations seem to be pretty common in classifications of simple singularities. So if you go to the list of singularities, I will not cite them all, but Mon from 2 to 3 or Riegers from 2 to 2 in the dimensions. there are many more. You can go to those lists and check which of them are augmentations, and you will realize that they are pretty common. So we think one of the interests that we have in these things are that maybe they are useful to classify map genres. Okay. Okay. So let me show one example with the same thing that before. I have the cusp. I build its one parameter stable unfolding. This thing is stable. It's just a cross cap. And for instance, I pick this function g. And what happens to the unfolding is that this cross cap becomes something like this, like old telephone. But you can see the parabola that's coming from the augmenting function, the g. So this is a bit what you need to have in mind. So you get the negative part only, and then you go through it in a parabolic way. Okay, so this is what's going on graphically. And then, of course, you could, instead of set square, you can put like any function that you want, and we will see that we can recover interesting examples. Okay, so I would like to use Damon's theorem on these things. And in fact, it's very easy, very easy. I'm going to reuse this thing because if I have a one parameter stable unfolding, and this is going to be x lambda goes to f lambda of x lambda, then I can always recover the augmentation as a pullback in this way. KB. So I can put here this mapping. Okay, so these two maps are transverse. This is a Cartesian diagram. And then if you do the computations, it's very easy to see that actually down here, the pullback is just the augmentation area. Okay? And I don't really care about the mapping here, but it's also very easy to obtain. Okay, so this is great news because then I can apply Damon's theorem to understand the A normal space of this thing. And if you do a bit of computations, then you can get that actually this is isomorphic to this thing right here. I'm going to be writing it like this. If pi is just the projection, over the last component, so this gets x lambda and goes to lambda. Okay, then this is isomorphic to this thing that I have here that I'm not going to be risking doing wrong. Okay, so the projection over the, so this will be d pi, over the liftable vector fields of F, plus the Jacobian ideal of G, plus an ideal, this ideal right here. Okay? So this in this case, this is just P plus 1 plus D. So this is just actually a quotient of a ring over an ideal. And this is nice because you have multiplication here, and this allows us to do some computations that we could not do in the module case. And yeah, let me just substitute this. Instead of putting here a pi, I'm just going to put the capital lambda. Okay, so I will use this as a projection. And in general, I will put this instead of theta pi. Okay, so there is a special thing that I want you to realize here that is important. That is that this ideal here is just the projection of the liftable vector fields over the last component. And this lives in OP plus 1, actually. This thing lives, is the Jacobian ideal of G, so this lives in OD. And this thing lives in the common ring, okay? So if I could somehow separate this ideal into the ideal generated by lambda and G, then it would be nice because then I could separate this into a tensor product and then study the two things separately and understand it better. So in general, when will this happen? Notice that remark. Remark, this ideal equals this other ideal. If, well, at least if either G belongs to the Jacobian ideal, so in particular when G has isolated singularity, when it is, yes. Oh, sorry, the augmentation. Yeah, thank you very much. This is important. This is the normal space of the augmentation, of course. This is the interesting thing. Okay, thank you. Thank you very much. So, of course, if G belongs to the Jacobian ideal, then this separates. And also, when capital lambda, so the parameter belongs to the projection over the lift all vector fields. Okay? So, yeah, if this is when G has isolated singularity, this means that G is quasi-homogeneous. Then Houston, in 2004, he said, okay, let's give this a name. This is going to be that F is substantial. Okay, this is purely technical condition, no geometrical intuition before, just something that allows us to separate this into two things, okay? And whenever I say in the hypothesis of a result that either G is quasi-homogeneous and isolated singularity or F is substantial, you need to think that what's going on in the proof is that this separation plays an important role, okay? So I'm going to give the first example of this, which is this result that allows us to, well, to compute bounds for the codimension of an augmentation. Okay. Theorem. Let F be a smooth map germ with one parameter stable unfolding and G function with isolated singularity. Then the codimension of the augmentation is bounded below by this product. Okay, and this lower bound is due to Houston in 2004. Okay, and then what we did was to find an upper bound for the codimension. So okay, in terms of the Zurina number and the Milnor number of the augmenting function, so of the G. So this is what Raul and I did, actually, again, using the explicit description of the module that the Damon theorem gives. And then with equalities, if G is quasi-homogeneous, or in the lower bound, if F substantial. Okay. So this is the first nice result that we have. And with this, since I'm going a bit behind my schedule than I thought, there is a theorem that we can find. I'm going to quickly explain it. So let's do a brief detour. Very brief. If F is a complex map germ from Cn to Cn plus 1 in the nice dimensions, okay, so if F being in the nice dimensions means that I can always perturb F to find a stabilization. So I can always perturb my singularity so that everything that appears becomes stable, okay? So when you have this, and ft is a stabilization, if ft is an stabilization, then the homotopy type of the image intersected with a small ball for t very small, this has the homotopy type of a wedge of spheres, and the number of spheres does not depend on the stabilization, and it's called the image Miller number. Okay. Sorry, of mu I spheres, Sn spheres. And this is called the image Milnor number, okay? So the number of spheres resonates with the number of spheres in the hypersurface case, so the Milnor number for hypersurfaces, and this is well known, that for hypersurfaces, it is well known that the Milnor number is always greater than the Turina number, and this is very easy to compute once you have the algebraic description. But the problem is that for the mu I, there is no algebraic description. There is a candidate proposed by Bobadilla, Nuño Ballesteros, and Peñafort Sánchez, but we still don't know if that actually computes the image Milnor number. Conjecture. This is the Mond conjecture. And we do not know if the image Milnor number is always greater than or equal to the A codimension. Okay, so what we did with this upper bound is to actually show that theorem. In this particular case, when F is a complex map germ from Cn to Cn plus 1, if F satisfies the Mond conjecture and G has isolated singularity, then the augmentation satisfies, of course, if F admits a stable unfolding, this also satisfies the Mond conjecture. Okay, so if F satisfies the Mond conjecture and G has isolated singularity, then the augmentation also satisfies Mond conjecture. And to use this, we also use a result by Houston that he proved in Corran 1, and then Jiménez Ballesteros, Jiménez Conejero and Nuño Ballesteros, they proved that it actually holds for any rank. So this actually holds in any rank. Okay, so this reduces for map germs with one parameter stable unfolding, this reduces the Mond conjecture to non-augmentation. So, okay, this is the end of the detour. So I will again be assuming that F is from Kn to Kp, so I forget about this. Okay. So yeah, we also have some theorems because, okay, since the augmentation is built from a stable unfolding and an augmenting function, one may wonder, and also I'm writing them as subindexes, so the choice of a stable unfolding and augmenting function seems relevant. But one can wonder up to which degree this choice is relevant. Okay, so we have a first proposition. This is actually very easy to check, that if G1 and G2 are right equivalent, so they are equal after a change of coordinates in source, then the augmentations by these two functions are equivalent. Okay, this is very easy to check. And one thing that was a bit harder to check is that actually, if F admits F1 and F2 one parameter stable unfoldings, and G has isolated singularity, then if, well, I think I'm going to write this in the other blackboard because I'm going to run out of space. Yeah, of course, yeah. The conjecture also says that this inequality is only an equality if, well, it is an equality when F is quasi-homogeneous. Okay, we also talk about this, also do this in the paper, but I didn't want to write it all. But yeah, there is another extra part about if this is an equality when F is quasi-homogeneous. Yeah, thank you. Okay. So as I was saying, theorem. I'm going to write it again. If F admits F1, F2 stable unfoldings, G has isolated singularity, and either F1 and F2 are substantial, or G is quasi-homogeneous, then the augmentation does not depend on the stable unfolding. Okay, so this is very nice because, of course, the K normal space gives you generators that teach you how to construct stable unfoldings, but stable unfoldings are not unique. So this tells you, okay, if somehow you notice that all your stable unfoldings are substantial, then the choice of unfolding does not actually matter. Okay, and this is part of the paper in which we do all of this is dedicated to finding conditions ensuring that all stable unfoldings are actually substantial. And then I will talk about this in the next section. But this is related to small f being quasi-homogeneous. Okay, this is going to be the link with the next section. I just wanted to say this because these two theorems, because then there is the last thing I'm going to say about augmentations is the way to characterize them. Okay, well, I think I can use this part here. The last thing that I'm going to say is about how to characterize of augmentations. Okay, so there is this thing called the analytic stratum. of a given map germ, which is just the evaluation at 0 of all its liftable vector fields, okay? So this tells you in which directions from the origin your singularity has the same type as in the origin, okay? So you may have like a prism of singularities, and then the analytic stratum will have dimension 1. For instance, in the crosscap, you only have a crosscap at the origin, so the analytic stratum is 0, okay? So this measures the strata along which the singularity is the same type as in the origin of the function. And so there was this statement by Houston, which is by Houston in the same paper in 2004, that F is an augmentation if and only if it admits a stable unfolding, and this stable unfolding has analytic stratum of dimension non-zero. Okay, so this statement is actually false because there is a counterexample, which is this one. This is called C3 in Mond's classification of map germs from C2 to C3. And this actually satisfies that it has a stable unfolding with analytic stratum of positive dimension. And actually, if you do the computations using the two theorems that I told you a moment before, you can see that the only way in which this is an augmentation does not yield this singularity. So there is a very simple computation you can do to see that this is not actually an augmentation. So actually, the correct way to state the characterization of augmentations is not as beautiful, sadly. It's not as simple, but it gives you a nice way to understand what the augmenting function is and what the original map germ is if your map germ is an augmentation, okay? So the theorem tells you that F is an augmentation if and only if you can build a diagram like this, a Cartesian diagram. Okay, in which H is stable. So this should be Cartesian. H is stable, and I'm going to copy it. P is greater than capital P, and the dimension of the analytic stratum of this thing is actually equal to 2P minus capital P plus 1. Okay, this is the only way in which something can be an augmentation, and this is hard to use to discard that something is an augmentation, but it's easy to use to see, as I said, the building blocks of a particular augmentation in the case that it is, okay? So yeah, this is what I wanted to say about augmentations, and in the last minutes that I have, I'm going to be talking, as I said, about quasi-homogeneity in general. So, okay. Three. Quasi-homogeneity. So why jump to this thing from something so specific like augmentation? So okay, of course, while studying this kind of map germs, we had to do tons of examples because they are easy to do and it's fun to compute, and you get very big numbers very quickly. So it's always fun to do some examples. And as you have seen, substantiality seems to be a relevant property when studying augmentations, although we do not have a geometric interpretation. So we wanted to understand if there was anything telling you that, okay, this map germ may admit a substantial unfolding or it may not. And while doing examples, what we realized is that if you had a stable unfolding which was substantial and you augmented using a non-quasi-homogeneous function, then the resulting augmentation did not have a substantial unfolding. So somehow breaking quasi-homogeneity also breaks substantiality. So we thought, okay, maybe this is related to f, the small f being quasi-homogeneous. And then we realized, of course it is, because if there is a very, very easy way to see that if f from Kn to Kp is quasi-homogeneous, and it admits a quasi-homogeneous one-parameter stable unfolding f. Okay, so being quasi-homogeneous is translated into being quasi-homogeneous is an equation for some weights and degrees, but in the case that if everything is analytic, this is equivalent. F is quasi-homogeneous if and only if there exist Euler vector fields. Euler should be in capital. One in the target. So I'm going to write it like this. Capital X1 dp capital X p. And since it is a one-parameter stable unfolding, I need an extra variable, which I'm going to call lambda, again, as before. And then a vector field in the source. Sorry. Okay, with di dj wi positive integers such that they are f-related. So the differential of c equals eta composed with f. Okay? So this is equivalent. And if you realize, this means that eta is liftable. But in particular, you have that precisely the last component has lambda. So this in particular implies that f is substantial. Okay, so this tells you that if your map germ admits a quasi-homogeneous one-parameter stable unfolding, then that unfolding should be substantial. But as we said before, there are lots of unfoldings. So we do not know if the rest are quasi-homogeneous or not, because even if f is quasi-homogeneous, you can build non-quasi-homogeneous one-parameter stable unfoldings. But as it turns out, if f is quasi-homogeneous, theorem, if f is quasi-homogeneous, then every unfolding stable. So I'm going to write every one-parameter stable unfolding is substantial. Okay. So this is nice because this is actually, when referring to the previous counterexample, the easy way to do this, there is a complicated way to do it, to see that it is a counterexample. And to see that easily that it is a counterexample, you actually need this theorem also. Okay, so this is nice. this is a necessary condition for something to be for a map germ with one parameter stable unfolding to be quasi-homogeneous, but of course, most map germs do not have one parameter stable unfolding. What we also did is I'm not going to write the definition because it's a bit long, but one can generalize being substantial to unfoldings in more parameters, to stable unfoldings more parameters. Okay. So, yeah. The way, and if we do this generalization, then the theorem also generalizes to more parameters. Okay, in that case, you do not have that every stable unfolding is substantial, but a bit of a weaker condition, which is also easy to check. And then a very big family of map germs of stable unfoldings is substantial, and it's actually any stable unfolding that you can think of building in practice will be substantial. The ones that are not are very weird, but they also satisfy another condition we call weak substantiality that also applies. Okay, I will quickly say something about the proof because some remark. To prove this, the thing is that we had to see that every stable unfolding is what we call lambda equivalent to a normal form. Okay, and this normal form is substantial in this generalized sense. And then lambda equivalence preserves substantiality. Okay. And actually, what does it mean to be lambda equivalent? Well, it actually is a particular instance of something called another name, phi equivalence. I'm going to try to write the dates properly. Which was first defined by Favaro and Mendes, as far as I know of, in the year 86, and then was later worked by Mancini in the year 83. Okay, so I think I messed this year. I think I missed one. So Mancini had it in the year 83. I think this one was before, as far as I know, but I think I copied it wrong. So there is a year here. Sorry for the mistake. And then also by Mancini and Cidinha in the year 93. Okay, so this is actually in both of the studies that I did here, what I mainly work with Cidinha was on this particular instance of phi equivalence. And basically what this is an equivalent relation that preserves the parameter space in some sense, okay? So all stable unfoldings are A equivalent, but A equivalence does not care if you are an unfolding or if you are anything. So we needed something that preserved actually the structure of unfolding to actually see if substantiality was preserved. And the answer was actually lambda equivalence, and one of the biggest works, I think in my opinion, is that of Mancini, because she actually showed that this has this in some cases for phi. Phi is a function that you can choose. For some choices of phi, this has the structure of one of Damon's geometric subgroups. And basically this means that you have finite determinacy theorems. And yeah, this is nice. So I think I'm running out of time. 1 minute. So I'm just going to say that there is a partial converse to this, because of course I have a necessary condition, which is nice and it's computable, but I would need to know if the converse is true, and it seems to be true. Converse is true in the equidimensional case, co-rank 1, and when, we need to write it correctly, and when either F has multiplicity 3, which is a bit restrictive, but it's nice, or when the stable unfolding has a zero-dimensional analytic stratum. This actually does not depend on the stable unfolding for the same number of parameters. So yeah, our conjecture is that this may be true in general, but the opposite is a bit hard to compute. Another thing that I tried to do with Cidinha was try to generalize this argument to the co-rank 2 case, and she encouraged me a lot to try to do it, but I think the argument just doesn't generalize. So this is what I wanted to tell, and thank you very much. I will be glad to answer any questions you have.
Very much. Any questions or comments?
Thank you for very nice talk. I have a question. Do you have any idea what could be the criteria for quasi-homogeneity for maps if you have the definition that it in some coordinate system in a source, in a target, it is quasi-homogeneous?
Could you repeat
Yeah,
that?
because quasi-homogeneity, you have some coordinate system, or you have some, yes, but you don't know which coordinate system, but the map is quasi-homogeneous. Do you have?
You are totally right. This is up to coordinate change. Of course. When I mean quasi-homogeneous, I had a problem with this because to me, I wanted to do a distinction between being weighted homogeneous as actually having a coordinate system in which the weights and degrees exist and that, and then quasi-homogeneous to be something equivalent to that. So in some coordinate system, they exist. But actually, the referee told us that this distinction is not very standard, so that we should just use quasi-homogeneous and always ask for coordinate changes. And I forgot to write it here, so you're totally right, that this is up to coordinate change. So if F is equivalent to a quasi-homogeneous map germ, then also every one parameter stable unfolding is substantial. And here too, the converse is also up to coordinate change.
Because we have in the past with Żytomierski such criteria, but only for varieties, but not for maps. If a variety is quasi-homogeneous.
Okay.
So therefore I'm asking, it is about this criteria, about these vector fields that you have, these Euler type vector fields. Yeah. So.
And you mean that if there's something similar would happen for varieties?
Yeah.
I mean, that would be nice to check. What I think is it would make sense to just study the formations of varieties and see something similar happen. I think it's something that has to do with the fact that the forming in the direction of the parameter, that's something. But I really have no idea of the geometrical intuition of what's going on. I would love to know more about this if anyone has any idea.
You have to look at the eigenvalues of these vector fields, of the linear part.
Totally.
Yeah,
This is based on looking at eigenvectors of the linear part using Poincaré Dulac normal forms. And this is, especially in the converse part, you need to do these computations of the eigenvalues, which are really important. And actually, the fact that we have only been able to prove this for co-rank 1 equidimensional is because this is when we know exactly what the eigenvalues can be and what shape do the vector fields can have. And it's a very particular. So we actually use the explicit description of tangent vector fields to the discriminant of stable mappings. So this is important. Yes. Thank you very much.
Thank you very much.
Thank you.
Any other question, comment? Well, I have a comment. The converse actually is a bit stronger. The theorem we have is a bit stronger than the converse of that. We prove that if there exists one unfolding which is substantial, then it is quasi-homogeneous.
Yes, exactly. Yes.
So the conjecture is with...
If there is one substantial, then it is quasi-homogeneous, and by the theorem, all should be substantial.
Yeah, so
we think that is
only,
what happens, but yeah, we are a bit stuck in the converse.
Okay, so thank you very much, Neto.
Thank you.
Let's thank the speaker again. Muy lento.
Muy lento.
Al principio ha sido muy lento.
Al principio de muy lento.
Sí.
Bueno,
Que de hecho se te ha comido tiempo, ¿no?
es lo que me ha faltado de explicar el ejemplo.
Ya, sí. Ah, sí, tenés. Ah, ya.
El ejemplo.
No, pero bien. No, a ver, así la peña lo he podido seguir. Para mí lento porque la gente así... pues,
Me traba muchísimo. Es que me ha sabido.
no te has trabado.
No, ha habido varias veces que en vez de stable he dicho unfolding.
Sí. Okay, so let's continue with this morning's Valencian session. It is a pleasure to introduce my friend, colleague, and boss, Juan José Nuño Ballesteros, who will talk about the topology of complex math germs and the general Le-Groyel formula.
Good morning. So first of all, I would like to thank the organizing committee and also the scientific committee for the invitation to participate in this 19th edition of the workshop. And as it could not be otherwise, my first words are in memory of our dear Cidinha. So around this time last year, many of us were here attending the Valencia workshop. And just at the very first day of the workshop, we received the sad news about her passing. So just a few days earlier, I had lunch with her and with her husband, Gaspar. So the news came as a complete surprise, and it was very painful for all the participants. And as I mentioned yesterday in the video tribute to Cidinha, so I had a very close relationship with her, as well as all the group of Valencia. And for that reason, it's a great pleasure and an honor for me to participate this year and to take part of this tribute. At the same time, and with Cidinha's permission, I would also like to pay tribute to another outstanding mathematician who made fundamental contributions to the singularity theory and who passed away in November last year, was Professor Le Duntran. So Le, together with José Seade, is one of the co-authors of the work I am going to present today. So I would also like to take this opportunity to remember him as well. Okay, so let's start. So I will make a short introduction, then I will explain the main theorems of the Le-Groyel formula type. In the third part, I will give an algebraic formula of how to compute it. And finally, we will pass to my favorite part, which is examples, okay? So what's the classical Le-Groyel formula? This is a formula that was obtained independently by Le and Groyel in 1973. So it gives a formula which relates the Milnor number of x plus the Milnor number of y. This is equal to some dimension. Here, x is an isolated complete intersection of dimension n in Cn plus k, which is given by k equations. And y is another ICs, which is obtained by adding one more equation. So it has dimension n minus 1. On the right-hand side, this is the relative Jacobian ideal of the function g in x. So this is the ideal in OX, which is generated by the maximal minors of the Jacobian matrix of both of f and g. Okay. Well, what's the Milnor number? The Milnor number of analysis was a generalization which was made by Ham in 1971 of the Milnor number of a hypersurface. So you take a regular value, a small enough regular value, and take the fiber and intersect with a ball, a small ball. Then it has the homotopy type of a bouquet of spheres, and the number of such spheres is called the Milnor number of the ICs. And the right-hand side of the formula has another nice geometrical interpretation. So this can be seen as some kind of Milnor number of the function g restricted to x, which by definition is the Milnor number of g restricted to the fiber of f. At all singular points you sum up, then you get a number. And here, the Milnor fiber is smooth, so this is the classical Milnor number. So this is the usual Milnor number because F, the fiber of F is smooth, okay? Well, with this notation, this Legros formula, classical, is mu of x plus mu of y equal to mu of g restricted to x, okay? Other Legros formulas, or other formulas of type Legros. So the first one is for space curves. So this is a work I did in 2008 with collaboration with Tomasella. So you take a space curve, x, reduce the space curve, and take any function, g, on the curve, which is finite. So the formula gives that the Milnor number of x plus the degree minus 1 is equal to the Milnor number of g. Here, the Milnor number of the curve, this was defined by Buchweiss-Greuel in 80. And when x is smoothable and xs is unsmoothing, then the smoothing has the homotopy type of a bouquet of one-dimensional spheres, and the number of such spheres is called the Milnor number. So this number is independent of the smoothing, and this is very similar to the case of an ISIS. G?
Maybe the power of the function?
No, just finite. Only finite. Yeah. So G, do you mean G? No, because X is one-dimensional. So if it is reduced, yes, no, doesn't matter. Okay. So this mu of G, this is called the Milnor number. It was defined by Goryunov, and so Goryunov was for curves in C3, and the general definition was given by Mond and Van Straten. But again, when X is smoothable, if you take any extension of G, then this number can be seen. It has the property that this Milnor number is equal to the sum of all the Milnor numbers, the classical Milnor numbers of G over the smoothing. So this is a smooth object, so this is the classical Milnor number, okay? Again, this is well defined, and this is independent of the smoothing. So if you take a smoothable curve, you can take this as definition, but the general definition you can do by using the dualizing module of Grothendieck, and it's more sophisticated. When you have a zero-dimensional ISIS, then by convention, the Milnor number of the zero-dimensional ISIS is this number, is the degree of G minus 1. So it's the number of points when you deform minus 1. So the formula you can give this in this way, this mu of x plus mu of y equal to mu of g. So this coincides with the classical Legros formula when the curve is ISIS. So for curves, our formula is an extension of the Legros formula when you don't have an ISIS, okay? Another one is for isolated determinantal singularities. So determinantal singularities were presented by Helen yesterday. Very nice talk. And this is a work I did with, again, with Tomasella and with Bruna Orefice Okamoto. At that time, Bruna was our student, and this was part of her PhD thesis. So you take an determinantal singularity. This means that you have a variety in Cn, which is defined by the zeros of the ideal generated by the S minors of some matrix of size Mn, but the codimension of the variety is the expected one. So this is equal to n minus s plus 1 times n minus s plus 1. And we also assume that it has isolated singularity. So in these conditions, if the dimension of the ambient space is less than this number, this is the codimension of the singular part of the generic determinantal variety. So in that case, X admits what is the so-called determinantal smoothing. So determinantal smoothing, you have your matrix F, and you deform the matrix a little bit by taking some generic constant matrix A, and then you compute the determinantal variety given this way. So if A is generic enough, this is smooth, and this is independent of the choice of A. So, but this is smooth, but what is different in this case is that in general, this determinantal smoothing is not a bouquet of spheres of the same dimension. You can have homology in several dimensions, so it is not a bouquet of spheres. This was discovered by Damon and Pike in 2014. So in this case, we cannot speak about Milnor number, but instead of it, we define the vanishing Euler characteristic. So the vanishing Euler characteristic, by definition, is -1 to the power d of the Euler characteristic of the smoothing -1. So here, d is the dimension of x. And in the case that you have an ICIS, an isolated complete intersection, so this coincides with the Milnor number. So this is an extension of the Milnor number in the case that you have a determinantal singularity. If now you take a function g over x, which has isolated critical point, then the special fiber y, you can consider it as an isolated determinantal singularity in some sense. So in some sense, because it is determinantal, but not in a smooth ambient variety, but in a singular ambient variety. And then we prove this Legros-Euler formula for determinantal singularities, which is that the vanishing Euler characteristic of x plus the vanishing Euler characteristic of the fiber is equal to this Milnor number of g, and by definition, this again the same. This is the sum of all Milnor numbers of the function g over the smoothing. So the smoothing is a smooth object, so this is the classical Milnor number. In particular, this doesn't depend on the smoothing. So it only depends on g and on x. Well, one more. So this is the Legros formula for image Milnor number. So this was a joint work with my former student, Irma Pallares Torres. So we consider a hypersurface in Cn+1, which is given by the image of a mapping F from Cn to Cn+1 with isolated instability. So here is some finite set, so the hypersurface can have several components, okay? Now, if you take a stable perturbation of F with image XS, then this intersected with the small ball has the homotopy type of a bouquet of spheres, dimension n, and this number of spheres, this is called the image Milnor number. So this was introduced by David Mond in '91. So the previous talk by Nacho was introduced this number also. In this case, so this hypersurface is never smooth, unless the trivial case that we have an embedding, but in general, this is not smooth. So this is an example. This is the H2 singularity, which is parameterized by xyq, xy plus y5. So this is in the Mond classification, this is called H2, has codimension 2. And a stable perturbation can be given in this way. This was due to Marar and Mond in '96. And here, the image has the homotopy type of the image Milnor number is equal to 2. And here you have two images of two pictures of this singularity. One of them is computer generated, and the other one is called here. They call it the koisa, the thing. So you can find in the garden here outside. Okay. So this is exactly the image of the perturbation. Okay. So the two spheres you can see, because you have a small pocket here. This is one of the spheres, and the other one is on the other side, on the hidden part of the image. Okay. Well, if you now take a generic hyperplane H given by a generic linear form P, Then the Algebraic formula says that the image Miller number of X plus the image Miller number of the generic section is equal to the Miller number of P restricted to X, which is by definition the number of critical points of F restricted to the stable perturbation. So here, the stable perturbation is not smooth. So you can look at the critical set in the stratified sense. So you have to count all critical points on each strata of the stratification. Okay. So let's go to the general formulation of the Algebraic formula, but the main difficulty is how to define the Miller number for a variety and also the Miller number for any function. So if you have a variety in general, you don't have a Miller number. If you have a function, in general, you don't have a Miller number. So you take X analytic variety, any analytic variety, and you take F, a mapping from X to CK with K components. You take representatives, X representative of the germ of the singularity, and take open subset in CK containing the origin, and take a representative of the mapping. Then we can always consider a stratification of F. A stratification of F means that we have a Witness analytic stratification of the domain, a Witness stratification of the target, that for each stratum in the domain, there is another stratum in the target, such that the restriction, the image is contained, and the restriction is a submersion. This was proved. You can find a proof. This is I think it's a folk result, but you can find a proof in this paper by Darfy. And what's the discriminant? The discriminant you can think as the set of critical values of the mapping, no? But the problem is that here, any restriction is a submersion. So you define as the critical value set, this is empty set. So it's better to define in this way. The discriminant is defined as the union of the closures of the strata in the target, which have dimension less strictly than K. Okay? So by definition, this is a closed analytic subset of dimension less than K. Now the restriction becomes a stratified submersion onto a connected open subset of CK. Okay? But the problem is that this mapping is not proper. So we cannot use the Tom Mather's first isotopy lemma to conclude that it is a locally trivial fibration. Okay? By definition, we say that F admits a Milnor-Ley fibration if there exists small enough epsilon and delta such that this restriction to a small ball in the domain and a small ball in the target, this is a stratified locally trivial fibration with the induced stratification. And the fiber is given by the inverse image of a value which is not in the discriminant intersected with a small ball. Okay? Now, this mapping, this is proper because we have the ball is a closed ball. So this is now a proper mapping. Then by the first isotopy lemma, a stratified locally trivial fibration is equivalent to a stratified submersion. So the only thing we need is to prove that this is submersion when we take the induced stratification. So the induced stratification, you have strata which are in the interior of the ball, so this is not problem because this is a submersion, but you introduce new strata which are in the boundary of the ball. So this is the problem. You have to control that it is a submersion when you are restricted to the strata in the boundary, in the sphere of radius epsilon. Okay. So examples, when you have isolated hypersurface singularity, so you always have Milnor-Ley fibration. This is the original Milnor fibration. And in this case, the discriminant is obviously the origin only. For ISIS, this was proved by Ham, that you have Milnor left vibration, and in this case, the discriminant is now, it is the set of critical values, okay? But in general, there are examples. This is an example from C3 to C2 of a mapping which doesn't admit any Milnor left vibration. So this was proved by Le, but it appears in a paper published by Sabat in '83. Okay. Okay. Now it appears in action the Thom condition. This was used by the talk of Aurelio yesterday. So Thom condition says that if you have a pair of strata S alpha and S beta with S alpha included in the closure of S beta, and for any sequence xn is, okay, I think it's a mistake. It's the opposite. If the sequence is in S alpha converging to a point in S beta, if the kernels of the differentials converge to some plane, then the kernel of the differential in the limit is contained in such plane. Okay. And the good news is that if you have Thom condition, then you have Milnor left vibration. So you can ensure that you have the stratification, you have submersion on the boundary, and then you can apply first the isotopy lemma, and then you get a Milnor left vibration. So this is a way to provide a vibration to a mapping, okay? So this is a well-known theorem by Le that any function, when you have only one function, when you have only one component, this always admits the Milnor left vibration. And in fact, any function satisfies the Thom condition for any weighted stratification of X. And in this case, the discriminant is obviously the origin. So this, I think this is, I'm not sure if this is the best reference for this fact, but in this, I put this reference. This was proved by Briançon, Maisonneuve, and Merle in '94. Okay. So just arbitrary, any variety. And the function is any, and well, non-constant function, because if it is constant, then the vibration is empty, okay? Yes, if you admit the empty set as a vibration, then this is a vibration. So what is the strategy? The strategy is to start with any function f, which admits Milnor left vibration, and then take another function g, which is good enough with respect to f, and such that the pair gf also admits a Milnor left vibration. So this is the strategy we're going to use. So we take a function f, we fix a Thom stratification of f from X to C with some strata S equal to S alpha in X, and of course, only two strata in the target, such as the origin and the complement of the origin. So we say that another function g has isolated singularity with respect to f if it has isolated critical point in the stratified sense with respect to S. Okay, it's a very natural condition. So from now on, we assume that G has isolated singularity with respect to F, and then we fix the pair GF, we call it phi. This is mapping from X to C2. We take representative as usual. Then with the above notation, we have the following, that this object, this is the critical set of phi in the stratified sense, but we remove the strata which are the components which are contained in the inverse image of 0 and take the closure. So the result is that this is a curve. This has dimension 1. And this is called the relative polar curve. Okay, so this is the first result. The second one, sorry, this is also a mistake. This should be capital gamma, not small gamma. The second one is that the restriction of phi to this relative polar curve is a finite mapping. In particular, the image is also an analytic curve in the plane, and this is called Serf's diagram. This is the name that both names were used by Le. And finally, we get that phi, the mapping phi, admits a Thom stratification S prime and T, where S prime is a refinement of S, and here the discriminant is given by this curve, is the Serf diagram together with the first axis of the plane, okay? In particular, with these conditions, phi admits a Milnor-Left vibration. So if you have any function, and you have a second function which has isolated critical point with respect to the first one, then the pair admits a Milnor-Left vibration, okay? Okay, so in the example of Le and Sabat, it's not difficult to see that if you take so this should be the first function, the x squared minus y squared z, and you take any stratification of this, then the second function, which is y, has not isolated critical point. So you cannot apply the theorem in this case, okay? Okay, we need one more ingredient, which is the notion of relative morphification of a function with respect to another function. So we have f and take another function g. So what is a relative morphification of g with respect to f? So this is a one parameter deformation of the function, capital G, which is of the form g of xt equal to g sub t of x, such that g0 is equal to g, so this is a deformation of g, and for t distinct from 0, this is a Morse function on the fiber of f in the stratified sense. So in the fiber, we have the induced stratification, and we ask that this gt is a Morse function in the stratified sense. And the theorem is that with the conditions that we are considering, that G has isolated critical point with respect to F, then G always admits a relative morphification with respect to F. Okay? Okay, so from now on, we assume that G has isolated critical point and fix a relative morphification, capital G. So this is the notation. S prime is the induced stratification on the fiber, and alpha is the dimension of this stratum. Delta alpha is the number of critical points of GT restricted to each stratum. L alpha, this is the complex link of the stratum, and we also call the half links in this way, L alpha plus minus. Here, dk is a closed disk of real dimension k. So the theorem is that the fiber of F is homeomorphic to this product. This is the fiber of the pair of GF times a closed disk of dimension 2, to which one has attached delta alpha spaces of this type. This is the pair of the disk and the boundary of the disk times another disk of dimension n alpha, and this is the cone of the union of the two half links, and together with the negative half link. This for all strata is prima alpha. Okay, another notation. This is the same, but we introduce also this number m alpha. This is -1 to the power n alpha, the dimension of the stratum, of the Euler characteristic of the pair given by the cone of the complex link and the complex link, and then the difference between the Euler characteristic of the fiber of F and the Euler characteristic of the fiber of the pair is given by this sum. This is the sum of all number of critical points times the multiplicity of each stratum. So you have to do this for any strata. And this is the general version of the Legge-Royal formula, okay? Well, here, the delta alpha, this depends on G. So this is the number of critical points of the morphification on each stratum. And the M alpha doesn't depend on G. This only depends on the fiber of F. Okay, this is just a corollary of the previous theorem, and the previous theorem, the proof is a little bit technical, but it's only based on stratified Morse theory. Okay. Yes, sometimes, but this is a difficult problem. So I have also some experience with monodromy in a very specific case, but of course, this is one of the other works which were developed by Le. So you can have the carousel, and then there is a way to control the monodromy, but this is even more complicated than this. Okay. Okay. So with this corollary, it's not difficult to see that all the Legge-Royal formulas that were presented in the introduction are particular cases of this formula. Okay. So this generalizes all known Legge-Royal formulas that we have presented at the beginning. Okay. So this is of course, this is a topological formula, but one question is, if I give you an example, so how to compute it? So complex, with complex varieties and complex mappings, it's not easy to compute topological things because it's not easy to make pictures, but the good thing is that with complex, sometimes you have a strong connection with algebra. So a good thing should be to have an algebraic formula for this Legge-Royal formula. Okay, so this is this part, but unfortunately we have to restrict ourselves to the case that the ambient manifold X, the ambient variety has isolated singularity and has pure dimension n+1. So we assume that X has isolated singularity, pure dimension, and you take G and F as above. So they are holomorphic functions, and we only assume that G has isolated singularity with respect to F. So F can be any function, but G has to be isolated critical point. Okay. So we have this formula that the Euler characteristic of the fiber of F minus the Euler characteristic of the fiber of GF is -1 to the power n of this dimension, the dimension of OX over, this is the ideal generated by F, and this is the relative Jacobian of GF and the saturation of this Jacobian ideal with the function F. So this is very nice because this is some kind of intersection number. So you can see this F, this ideal generated by F, as a hypersurface in X. And this is exactly the equation for the relative polar curve. Then what we are computing is just the intersection number of the hypersurface given by F and the relative polar curve in the ambient variety X. So here, this is J I infinity is the saturation of J with respect to I, where I and J are ideals in some ring. So by definition, this is the definition of saturation. And the relative Jacobian ideal, the definition is this one. So if X has defining equations phi1, phi k, then this is the idea generated by the capital N minus D plus 2 minus of the Jacobian matrix of phi, G, and F. And you take this ideal and you put into the local ring of X. Okay. So when X is smooth, when X is equal to Cn plus 1, and both F and the pair GF define ICs, so this saturation gives the same ideal. So we can recover the classical Lie-Grover formula for two functions. Okay, so this algebraic formula is a generalization of the classical Lie-Grover formula. And if you consider more functions, you take F1, Fk, and G, then we can use a similar argument, but in this case, you have to take X as the variety given by the first k-1 function. So in this case, this is not smooth, but you have isolated singularity. Okay? Okay, so let's go for examples, the last part of the talk. So the first example, we consider this H2 singularity, Koisa. So this is the surface I presented in the beginning. It was due by Marar-Mond, 96. But because we need to take a intersection with a generic plane, I have to perform a generic slice. It's better to take a different parametrization. So this is a different parametrization that we found this parametrization in 2014 with collaboration with Marar. So this is A equivalent. This is the same surface with different coordinates. This is yq minus sy and y4 plus xy square plus xy minus sy to the square. But if you take x equals 0, you get y3 and y4, which is the E6 singularity. So this is the generic section of this surface. Okay. So to apply your formula, we have to define which is the variety, the ambient variety. So the ambient variety is the hypersurface in C4, which is given by all, not only the image of H2, but all the images of the stable perturbation. So you take all the family and you consider it as a hypersurface in C4. And the functions in this case are two projections, Fg. F is the projection onto the parameter S, and G is the projection onto the variable X. So the fiber of F is exactly the image of HS, of the stable perturbation. So we know that the homotopy type is a bouquet of two spheres. So the Euler characteristic is equal to 3. The fiber of the pair of G and F is the image of this plane curve. So this plane curve, for generic XS, we have a stable perturbation of the plane curve E6, and you get this picture. So in this case, it's not difficult. It's quite easy to see that the fiber has a homotopy type of 3 circles. So in this case, Euler characteristic is equal to -2. Okay, so it's 1 minus 3, which is -2. Okay, so now we compute the critical points of G on the fiber. So the stratification on the fiber is given by the stable types. So the 0-dimensional strata are triple points and Whitney umbrellas. But in this case, if you look at the picture, we have here 1 triple point and 2 Whitney umbrellas. One of them is here, and the other one is on the other side. Okay, so we have 1 triple point and 2 umbrellas, 2 Whitney umbrellas. These are the critical points on the 0-dimensional strata. In both cases, the complex link, which is the complex link for the triple point, to compute the complex link, you take a generic hyperplane, a generic two-plane in this case, and you take a slice through the origin, and now you move a little bit the plane. So when you move a little bit the plane, you get something like this. So this is this has the homotopy type of 1 is 1. Okay, And then the multiplicity, which is the Euler characteristic of the pair, is 1 minus 0, which is equal to 1. And for the Whitney umbrella, we also have this. Again, you take a generic plane through the origin, and then you move a little bit the plane, and then what you get is this curve. And this curve, again, it has the homotopy type of one sphere, and then the multiplicity in this case is again equal to 1. Okay? So one-dimensional strata. So the one-dimensional strata is given by the double point curve. So if you look at the image, so the double points are all these curves. This gives a curve, which are the double points. This is the singular part of the hypersurface, which is not triple point with the umbrella. And at each one of these points, the type is a transverse double point. So singularity is something equivalent to this. Okay. So in general, this curve is difficult to compute in the target, but is easier to compute in the source using the parametrization. So by using the parametrization HS, we compute the double point curve in the source in C2. So we use the divided differences. So we have to compute the points xy and xy prime such that the images are equal, but the points are different. So we divide by y minus y prime equal to 0. This gives two equations because the first equation is trivial. So, okay, so the parametrization is given in this way, but the x is the same. So you get exactly two equations, one for y and one for y prime. But now you have to eliminate the y prime. So when you eliminate the y prime, we get only one equation, and this gives a curve. So this is the double point curve. Okay. Here the s is a parameter. The s is a constant. So the variables are x and y. And the critical points on this stratum correspond to the critical points of the projection xy goes to x. So this is the picture of the curve, and here you get this figure, and you get at the critical points of the projection to the x. So we get, of course, the triple point appears, but they are singular points of the curve, so we don't take into account these triple points. The Whitney umbrella, which are in the yellow color, we have two, one here, another one here. They also appear as critical points, but we don't consider them. And finally, the other critical points, we have 4 in green color, one here, 2, 3, and 4. So there are 4 critical points. But remember that we are in the source, and the mapping on the double point curve is 2 to 1. So in the target, there are only 2 critical points. So there correspond to 2 critical points on the image. Okay, and what is the complex link in this case? So to compute the complex link, in this case, because the stratification, here the stratum has dimension 1, first you have to take a normal slice. So when you take a normal slice, you get a A1 singularity, and now you compute the complex link. The complex link, you take generic line through the origin, and then you move a little bit, and you get 2 points. So in this case, complex link is equal to 2 points. Okay? And again, the multiplicity, of course, the cone of 2 points, sorry, there is a mistake. This is the cone of the complex link and the complex link. So it gives 1 minus 2, which should be minus 1, but because we have a correcting sign, then finally we get the right multiplicity, which is 1. Okay? And finally, two-dimensional strata. But the two-dimensional strata is the regular part of the image of HS. But if you compose the projection with the parametrization, we get the mapping X. So we have no critical points on this stratum. So finally, the difference between the Euler characteristic is 3 minus 2, which is 5. And the critical points, we count 3 in the zero-dimensional stratum and 2 on the one-dimensional stratum, which gives 5. So the formula is okay. So this is an example of the topological formula. This is not the algebraic formula. This is the topological version. Okay. One more example. This is a very easy example. We take as ambient space the free space C3. This is smooth space. And you take two functions, G and F. So F is X, Y, Z, which gives the triple point. So the fiber F, the zeros of F is the triple point in C3. And the function G is X plus Y plus Z. So it's not difficult to see that this function has isolated critical point with respect to F. The fiber of F is not difficult because if you take X, Y, Z equal to some constant, which is distinct from 0, so one of the three variables should be distinct from 0, so you can, the three variables should be distinct from 0, and you can get one of them in terms of the other two. So finally, the fiber is diffeomorphic to C star times C star, which has the homotopy type of S1 of the torus, S1 times S1. And the Euler characteristic is 0. The Milnor fiber of G and F, if you substitute here Z equal to minus X, XY, no? You get this function. This is a plane curve. This is the D4 plane curve. So Milnor number is 4, and the Euler characteristic is 1 minus 4 equal to minus 3. Now we use the algebraic formula. For the algebraic formula, you compute first the Jacobian ideal, which is given by the 2 by 2 minors of the Jacobian matrix of G and F. And then you take the saturation ideal. The saturation ideal, in this case, is very easy to compute by hand. You get Y minus Z and Y minus X. And now, finally, the dimension of this quotient, you get the dimension in O3 of X, Y, Z, which is F, and the saturation of the Jacobian ideal. And this is very easy to see that is equal to 3. Okay, so it coincides with the difference between the Euler characteristics of the fibers. Okay. Okay, and just to finish, one more sophisticated example. So in this case, I think it's difficult to do by hand or to do by a picture. So it's important that in this case you can use computer. So we will, by using our formula and by using the computer, we can compute the Milnor number of a surface in C5, which is defined by Pfaffians of a skew-symmetric matrix. So the entries are functions in O5, and the matrix is skew-symmetric. When this has dimension 2, then it is well known that this is Gorenstein. This was proved by Bushbaum Eisenbud in 1975. But in fact, we have converse. Conversely, any Gorenstein surface in C5 is obtained in this way. This was a structure theorem by Bushbaum Eisenbud. If you assume now that X has isolated singularity, then it is also normal because this is Cohen-Macaulay and isolated singularity, and it is smoothable, and it has a well-defined Milnor number, which is defined as the second Betti number of the smoothing. So this xt is the smoothing, and this is smoothing is defined in a very natural way. This is taken as the Pfaffians of the matrix F, which is deformed a little bit with some constant generic skew-symmetric matrix A. So you take your skew-symmetric matrix and you deform a little bit the entries with some constants, then take the Pfaffians of this, and this gives the smoothing. Okay, so it's a very natural construction. So we compute, in this example, with singular, the Milnor number of a Gorenstein normal surface, which is given by linear Pfaffians. No, sorry, this is a mistake. So the entries of the matrix are linear. The Pfaffians are not linear, but the entries of the matrix are linear. And we show that in this case, the Milnor number is equal to 4. Okay? So this is the singular code to compute the Milnor number. So here we are in C5. So we have 5 variables, but we also have T, which is the parameter. So in total, we have 6 parameters. So this is, we define the matrix A, which is defined by taking random linear forms. So we assume that they are generic linear forms. We compute the Pfaffians in this way. And this is, the dimension is 3 because this is not the surface. This is the family of the smoothing. Okay, so it has dimension 3. Now we see that, we check that it's Gorenstein of codimension 3, so we take the free resolution, so it's easy to see that it's Gorenstein. This is the first function, is the projection onto the parameter, and x0, we take t equals 0, and we check that x0 has isolated singularity, and also that x is a smoothing. So for t distinct from 0, you don't have critical points, you don't have singular points. Finally, we take 2 generic linear forms. This is one, and this is the other one, and we apply our formula. And applying our formula, we get that the Milnor number is equal to 4. Okay, so by hand, this is, I think this is quite difficult to do, but using computer, when you have an algebraic formula, you can do it. Okay. Okay, so finally, I only want to thank the organizers for the change in the schedule for tomorrow, for today, sorry, so we can attend the football game. Okay, so thank you very much. Okay.
Thank you very much, Juanjo. Any questions, comments?
No, my question is the following. In the classical case, it is well-known theorem that if the Milnor fiber has trivial homology is trivial, then also the space is trivial. There is any hope that also in this generalized case, you have the similar statement, or rather not?
Well, in the general case, I don't think so. I think it's not. Yeah. No, but the problem is, of course, you can do, if you have a variety, then you can take a stratification, which is artificially, you can create examples where. Yeah. Isolated singularity, I think maybe in this case is true. I'm not sure, but I believe that in such case could be true. Okay.
Any other question, comment?
So can we divide the right-hand side of the Gravell formula, yours, into the contribution coming from FF and the contribution of FGF?
This one?
Or the previous one, your main, yeah. So can we divide the right-hand side
Yes.
into the contributions coming from the first term of the left-hand side? Right-hand side?
No, each term of the sum you have contribution of GT over the stratum and multiplicity, which only depends on F. So in each term of the sum, you can divide, but the sum, you cannot mix, you have mixed terms, so it's not possible to separate.
Yeah, just that's curious because in your first example, the H2 example, 3 and 2 is, we can find that the final computation.
This?
Oh yes, this is just a coincidence.
No, but both terms come from G and F.
Okay.
It's not, yeah, because of course the zero-dimensional strata obviously are critical points of G.
Yes.
So strictly speaking, they belong to G, no, to the pair, not only to F. Okay.
Okay, thank you.
Any other question? Then let's thank the speaker again. Ignore the vibration.